That's fine with me.
Okay. So let's start this evening EC Game Changers online seminar. So how mission changed the view of our universe. First of all, I would like to introduce a little bit EC. EC has been founded 25 years ago as an institute for international collaboration where people can come, sit together in a very informal way, interdisciplinary way, international way, and do science. It's an institute where actually people again sit together and do science. So what are the open scientific questions? And they come then with data, simulations, data analysis, interpretation, and the main goal is then to advance the science by using the different space data in a multidisciplinary way, not only in the ESA missions, but combining X-ray missions with infrared, radio, and multidisciplinary, and to publish them in peer-reviewed papers. In the 25 years of EC, of course, to serve the space science community, EC developed different tools. One of the tools are this international team, which is just what I explained to you right now, to come together and do science. Then we have workshops where we are publishing substantial review papers and publishing the space science series of EC book. And then we have other tools like informal open discussions, which are done in forums and so on. And of course, after 25 years of success, I have to say, and having more and more visitors coming to EC, around 1,000 or almost 1,000 per year, this was a hard year for EC because there was no face-to-face meeting anymore. And the question was how we can anyway still serve the space science community. And the EC Directorate came up with it should be data, it should be mission, and it should be science. So let's have an online EC seminar on game changers. And I am especially proud today to have Arvind Parmar here to give the talk on the XMM-Newton's, a new vision of the X-ray universe, which is an amazing mission. It has been launched in 1999, and after 21 years, it's still flying, even though the design lifetime was for 10 years, and it will still fly until 22. Let's hope even further. Arvind Parmar is a very known scientist around the world. When he was working at ESA on EXOSAT data, I mean, people in my research field like myself, I was reading his discoveries and his pioneering work done with EXOSAT data. And when I met actually Arvind, it was for me, it was something like, wow, I am meeting Arvind Parmar. So I'm especially proud to have you giving this talk. He was then involved in several ESA activities, also as the XMM mission manager. And he's now retired from ESA, I think after 40 years or almost 40 years or 40 years. I am sure everybody will miss you at ESA, and we are missing you at EC as one of the ex officio member during of the EC Science Committee meeting members. And he's currently on the board of trustees of the Royal Astronomical Society. And so I'm looking very much forward for your talk. I would like also to mention to all the people who are listening now, there are almost 125 already, and I am sure this number will still increase, that of course the video and audio has been muted and for all the participants. At the end, when the talk is finished, you have two way of asking questions. One is writing the question in the chat or raising your hand. But for us, for the questions, we are waiting for the end of the seminar by Arvind Parmar. Thank you.
Thanks, Maurizio, for those very kind words. It's a pleasure to give this talk, and thank you very much for inviting me. It's also actually the perfect day to give this talk, because December the 10th was the launch in 1999 of XMM. So it launched today, 21 years ago, a little bit earlier in the afternoon, but My screen seems to, oh, there we go. Okay, so the perfect day to give this talk. So what I'm going to do is give a little bit of an introduction to the mission. I'm going to then give some selected science highlights. And when Maurizio asked me to give this talk, I thought, great, fantastic, mission I know well, it's got wonderful science, etc. And then when I thought about it a little bit more, I realized actually how difficult it is to cover the science of XMM. There are over 6,000 publications, and how do you choose, the most important ones? So what I've done is selected the ones that I enjoyed the most. You'll probably have a different set, and that's fine. You can compare yours with what I've done. So what I've done is selected a small number of really, I think, really important science highlights from the mission. And I've tried to see how we measure the success of a mission. Why is XMM so successful, and how do we measure that? And what are the factors that make, in particular, XMM so successful? And then if I get the time, I'd like to talk a little bit about Athena, which is the successor mission to XMM, and see what lessons we've learned from XMM that can be moved forward to Athena. So that's the structure of what I want to talk about. So, as I said, launched today, 21 years ago, into a 48-hour orbit, an eccentric orbit by an Ariane 5. So it goes over the North Pole and then out to the south, effectively. It's had almost now 20 years of almost flawless operations. They've been, in the general, very, very smooth. It's a big mission. It weighs almost 4 tons. It's 11 meters in length, so it's about the size of a single-decker bus. And you can see this picture here to give you some idea of the scale of things. This was in the test center at ESTEC sometime before launch. It's operated from 2 sites. The mission operations, so the sort of more engineering type activities, are conducted from ESOC in Darmstadt in Germany. And the science operations, the interfaces to the scientists and more to the instruments and so on, from ESAC just outside Madrid in Spain. Like the other ESA funded missions, it's funded till the end of 2022, but it can go on. There's a possibility of further extensions and so on. So it followed EXOSAT, which was when I joined the agency, which was ESA's first X-ray observatory. And it has 3 large X-ray mirrors. You can see them in the top picture here covered, these 3 devices here. These are the star trackers, and the smaller device is the Optical Monitor. These have in total something like 4,000 square centimeters of effective area, 0.4 square meters. Behind them, well, there are 6 instruments in total, and they observe simultaneously. Each of the detectors, each of the mirrors has an X-ray imaging camera called EPIC, European Photon Imaging Camera. And this gives you about 150 EV, 100 to 150 EV energy resolution. So they're imaging spectrometers. It also has behind 2 of them X-ray reflection grating spectrometers. These give much higher spectral resolution, something like 200 to 800 over the 0.2 to about 2.5 keV energy range, so a narrow energy range. But they're not effectively imaging instruments, but they have very, very high spectral resolution. There is an optical monitor, which also works in the UV as well, which complements these instruments. And it's worth noting that these capabilities are very complementary to those of NASA's Chandra observatory. This was launched a few months before XMM. It has a smaller effective area, about 800 square centimeters, but it has a much, much better spatial resolution. So you get less counts, but you get better quality images, if you like. And the 2 are very complementary, and I'll try and stress times of that. You can see here on the details of the mirror, there are 58 nested mirror here that make up each of the X-ray mirrors, and this is one of the EPIC detectors here. So it's important to realize that XMM is an observatory. So the observing program is defined by the community. There are annual calls for observing time proposals, and these are peer reviewed. There is an observing time allocation committee, the OTAC. They meet once a year or so. It's quite big. I mean, there are about 70 members of the OTAC each year, and those people overlap. We try not to ask people too many times to do it. It's quite a lot of work. You get 50 or 60 proposals to look at, because the typical oversubscription in observing time is about a factor of 6. So each AO has something like 500 observing time proposals to look at. Something like 1,500 scientists participate in each AO. So, typically 3 scientists per proposal or something. And the job of the Science Operations Center at ESAC is to provide the documentation that you need to do these proposals, to provide a help desk, to do the scheduling, to do the coordination with other facilities. Many of the observations are coordinated, to implement rapid TOOs within a few hours if necessary, to work with the community and with the instrument teams on the data analysis software, the calibration, and to provide the science archive, which is the way that users access the data. It was also, it's worth pointing out, a users group. They play a key role in ensuring that the observatory, the services that we provide are improved in terms of prioritizing the calibration improvements, the software improvements, and so on. And they're a very important group, and they provide valuable advice to the project scientist. Just want to show you how much XMM had advanced, the technology behind XMM compared to EXOSAT. I mean, EXOSAT was 1983 to 1986, so it was launched 16 years before XMM. It was only 500 kilos as opposed to almost 4 tons. It was ESA's first 3-axis stabilized spacecraft, and we had a lot of problems with the pointing during the observations, and it was one of the first with an onboard computer. It had a similar orbit to XMM, a 90-hour orbit, and that allowed long interrupted observations. It had 3 instruments. It had 2 imaging instruments, but they were rather narrow energy range, and they had rather high backgrounds, so that they weren't perhaps as successful as we hoped they would be. And it had 2 non-imaging instruments that provided something like 20% energy resolution and 10% energy resolution. So not nearly as good energy resolution as the imaging instruments on XMM gave. The bottom picture there shows the control center where I, and I think Thierry and anybody else who was one of the EXOSAT duty scientists, spent a lot of time in our youth there. It was dark and rather dingy, but we had real-time contact with EXOSAT, and we could monitor the observations very closely and see what was going on in real time. And that was a very valuable asset that we had. I want to turn to one of the first results that I like very much. I'm going to put the results in order of distance away from us. And the first result was a set of joint observations that were made with Integral, mapping out the Van Allen belts. And this is not an observation that was sort of planned or uses any of the instruments I've talked about, but both missions have on board particle background monitor for engineering, essentially for engineering purposes. And because of their orbits, they go through the Van Allen belts, both the inner proton belt and the outer electron belt. And they've been operating together for 16 years now. And so this has allowed a big data set of radiation results that have allowed a dynamical model for the electrons to be produced between 4,000 and 60,000 kilometers, which is used now in operating the spacecraft, this spacecraft and others, and is a kind of lead-in into what we're going to see when the SMILE mission, which is a joint ESA-China mission, which is going to be looking at the aurorae and the Earth-Sun interaction and so on, which is scheduled for launch in 2023. So to me, this is a classic example of how creative scientists are. This wasn't part of the science payload, but already people were thinking about what science can I get from these other areas of the mission? And I thought that was a rather nice result. The other thing that's, I think, rather nice and unexpected is how XMM has contributed to solar system science. This wasn't something that originally was thought to be of high interest. You can see on the left the optical picture of Jupiter, and at the top you can see a UV image from STIS on board the HST, and you can see how dynamic the aurorae is in the UV from Jupiter. If you look on the right, you can see some Chandra images of the X-ray emission. Those are shown in purple of the North Pole and the South Pole. And you can see from the viewing geometry from the Earth, the North Pole was much better, had much better geometry than the South. We only see part of the South. But you can see the X-ray emission is also very structured when you look at it with Chandra. When you look at it with XMM, you can't obviously see so much structure. We have 15 arcseconds half energy with images as opposed to about less than 1 arcsecond imaging. What was surprising from the XMM and Chandra results was that the emission from the South Pole is pulsed with a period of about 11 minutes. So you can see the FFTs in the left-hand column here from Chandra, from XMM and from Chandra, from 2 different observations. And this big peak here, just over 10 minutes. That's surprising. We don't see a similar thing on the Earth. And on the North Pole, something different is seen. There is a lot of energy at different energies, but there is no one fundamental frequency that seems to be pulsing, which is surprising. So the North Pole and the South Pole seem uncorrelated on Jupiter, which is different from what we see on the Earth. There is a possible explanation for this, and it's due to the fact that we're viewing the 2 poles differently. We're viewing all of the southern, the northern pole. So we're potentially seeing that the northern aurorae are being fed by more than 1 regions from the magnetosphere, and these have different timescales, and they wipe each other out, so they produce erratic behavior. Whereas at the south, what we're seeing potentially is the aurorae being fed by just 1 loop, and so we're seeing the natural time of that, which is something like 11 minutes. So we may be seeing something due to the different viewing geometries, and of course we can test this in the future when we look again. I'd like to thank Mark McCaughrean for these view graphs, which I stole from some of the excellent presentations he gives to the SPC, this ESA's Science Program Committee. I want to turn now to our own galaxy, and to me, what has been one of the really nice results that's come out of the XMM mission. So this is a light curve of an X-ray binary called XB1916-043. This is the light curve here at the bottom panel, and it's using the EPIC instrument, and you can see it's something like 60 counts per second. And what you can see are these periodic irregular variations or dips in the X-ray intensity. So the X-ray intensity drops down very regularly, but not down to 0, but down to something close to 0. And occasionally you see these dips here at a different phase. This shows the hardness ratio. So this is a term the X-ray community uses. So it's basically the ratio of hard, which is 2 to 10 keV, divided by soft, which is 0.1 to 2 keV, typically X-rays. So essentially an increase in hardness ratio. So this means you're losing preferentially soft X-rays, so low energy X-rays in these intervals here. And these repeat with the orbital period of the system. And these intervals that are shown here in black are where we've used to measure the continuum. So the X-rays that are unaffected by this extra absorption that we're seeing. So how did we explain this? I mean, these sort of effects were seen in what I would call the EXOSAT era. The data, of course, wasn't as good. And we could simply model the changes that we saw during the dips as an increase in low energy absorption, photoelectric absorption, with a lower solar abundance than solar. And these were typically 10 to 15, and in one extreme case, 600 times less than solar. But those models fitted the data. The fits were good. They were consistent with what we expect, and that was very happy. We got better data in the mid-90s, ASCA, Becker-Sachs, RXT, and so on. And it was clear that the model that was applied in the EXOSAT times no longer worked. So a more complicated model, progressive covering, was introduced. And this had then two components. One was point-like, and that was covered or not covered. And then another extended area that was covered with a particular amount of absorption and a particular fraction of coverage. And put those two models together, and you could again fit the data. So, you know, the model had become more complicated, and that's good. I mean, that's what more data tells us. And then we had XMM come along, and we had the data that you just saw. And the great thing about XMM was not only could it measure the absorption of the continuum shape, but it could actually really start studying the line emission and the absorption lines that you could see. And you can see here a blow up of part of the ion line complex. So these are ion K absorption lines here, and some maybe a hint of nickel and so on. And what became clear, and this was pioneering work by Laurence Borin and Maria Diaz-Trigo, was that you could fit the spectral changes by photoelectric absorption, a photoionized absorbing plasma. And this is a rather complex, it's the most complex figure that I show in the whole talk. So let me walk you through it fairly closely. So there are three spectra. They correspond on the left to the persistent spectrum. So that's the spectrum away from the dips, which we think is unabsorbed by any extra absorption. And then the dipping has been divided into two, shallow dipping and deep dipping. And what you can see here is the spectrum at the top. And you can see the residuals down here. There is an emission line needed. And then there are these absorption features that you can see here. And those are modeled by some cold absorption and this photoionized absorption component here. And then the continuum is a power law black body in this absorption Gaussian. So the parameters of that are then fixed at the values that you see during the persistent emission. And then you fit the shallow dipping and you adjust only the absorber, the ionized absorber. And you can see here the parameters of the ionized absorber. This Kasai is the amount of ionization, and 4 is very high. And that effectively means that everything except for iron is pretty much totally ionized. And during the middle bit, you can see the absorption, the amount of absorption comes down, and the amount of absorption increases. But what's really interesting here, and you can see here's the deeper ion line, but what you can see here during the deep dipping, and again the ion line, you can see the ion line here, but now the absorption, the amount of absorption has decreased, and that is affecting the continuum. So what we're seeing here as a continuum change is actually the effect of lots of different photoelectric absorption of lots of different elements that we can't resolve in this data with CCD type resolution, but it's causing what we thought before were continuum changes due to simple photoelectric absorption are indeed much more complex. So now we're able to fit, we've gone back from started with a simple model, we went to a complex model during the Beppo-Sachs time. We've gone back to something simple again with a lot more physics in. And that's the beauty of XMM. It's really pointing us towards the physics of the mission. And I'd just like to put this in. It's not an XMM result, but it's lovely. It's a Chandra result on this same source, it's XB 1916. It's a very recent result. And what they've done is looked at the non-dipping intervals with grating spectroscopy at around silicon and iron, so quite high energies above the range of the XMM gratings effectively. And what they're seeing is blue shifted absorption, red-shifted absorption of these lines. And you're saying, well, okay, so it's the systemic velocity of the system. It's 220 to 290 kilometers per second. It's not that fast. But in fact, they see lots of other lines with zero systemic velocity. So what we're probably seeing here is actually gravitational redshift in an X-ray binary. So the absorbing material in this case is somewhere close to the inner edge of the disk. It's still fairly far out. It's at a R of about 1200 GM/c, but we're really actually beginning to measure where these structures are in the system. And I think this is a wonderful result, and it gives us a hint of what we're going to see when the next generation of missions comes along. So it's a Chandra result, but it's lovely. So XMM has done a lot of things with X-ray binaries and with other systems. And I think one of the things that it's completely revolutionized our understanding of is what are called ULXs, ultra-luminous X-ray sources. These are systems that are seen in external galaxies to our own. They're incredibly luminous. And the definition is if they're something more than a few 10 to the 38 ergs per second, which is the Eddington luminosity of a 10 solar mass black hole. So it becomes difficult to understand where these systems come from. And XMM has looked at many of them, and many of them pulse. And this was one of the classic examples. It was a ULX in an external galaxy called NGC 5907, and it's pulsed. You can see the pulse fraction here, very strongly pulsed with a pulse fraction of 1.43 seconds. So it's a neutron star. So the thinking now is that some of these systems are very highly magnetized neutrons with very beamed X-ray emission. And this has completely revolutionized our understanding of these systems. I mean, the great beauty of missions like XMM is the insights they give us into things like star formation and the structure of galaxies and so on. And this montage we put together when XMM and Herschel were flying. And this picture here shows in the infrared the yellow and the red what Herschel sees, and you basically see the star formation. You see material heated up to 50 to 100 Kelvin or so, and in the blue the X-rays, and the X-rays are showing us the end products of stellar formation, and you can see concentrated in the bulge and in the other regions of the two. And you have to put them together in order to understand these systems in total. You need to look in the optical, you need to look in the infrared, and you need to look in the X-rays. XMM, because it has these continuous observations, has done lots of very interesting observations of AGN, and some of these have been incredibly surprising. For example, this light curve that you can see along the bottom shows these unexpected 9-hour interruptions. It's almost like regular fairing from a fairly low mass black hole system in a nearby safer galaxy, GSN 069. It could well be it could be a transit of an object through the accretion disk that's causing eruptions, or it could be some sort of instability in the accretion flow. And it's intriguing to wonder whether these things would scale with higher mass. Most AGNs have higher masses than these. And so if the timescales scale in some way, it could well be that we've missed similar systems because we simply haven't looked long enough for these systems. XMM has, I think, revolutionized our understanding of AGN and the X-ray spectroscopy. And it's done this in a lot of cases by combining observations with NuSTAR. And this is an example. It's an I think it goes back to 2013. It's system NGC 1365. What you can see here is the X-ray spectrum between about 3 keV and about 70 keV, with the underlying power law taken away. So you're kind of seeing the residuals against the power law. You can see this broad feature here, which this is the iron line energy. So this could be an iron line. This is the NuSTAR data, which goes up to 70 keV or so. And this is the XMM data, which is better quality in this rather more limited X-ray range. And it's by putting together the two things that we really learn a lot about these systems. And what this told us, there were two models for this broad feature that we see at 6 keV and below. Relativistic reflection from a rapidly rotating disk, and that rapidly rotating and the relativistic effects give a lot of the width of the feature, or multiple partially covering absorbers that that add together to produce this broad feature. With XMM data alone, you can't distinguish between the two models, and you can see that up to here. The relativistic model is in red, and the blue model is the partially covering model, and you can see they fit equally well. Just from the XMM perspective, you can't tell. It's only when you put the XMM data together with NGC 1365 do you see that it's the relativistic reflection model that is consistent with the whole energy range, and that is the beauty of putting these two missions together. And indeed, there are lots of cases where that's happened. I mean, here is another AGN, PDS 456, which was looked at with XMM here and with NuSTAR here. And if you ignore the NuSTAR data, you can see that the XMM data seems to have this break here, but it's really difficult to model what's going on unless you have the underlying shape of the continuum, and you only get that by having the counts here. Can you see what the continuum is doing? It's really difficult to understand the physics of what's going on. And what's going on here is really interesting, because what it's showing is almost a classical P Cygni profile of an outflow of highly ionized gas. And this gas is being expelled at relativistic velocities from presumably the accretion disk. And the kinetic power in this wind is 10 to the 46 ergs per second in this case. So it's enough to provide the feedback, and the feedback between the AGN and the galaxy is one of the key questions that helps us understand galaxy formation and star formation and how that turns on and turns off and so on. And thanks to Norbert Schartel, the XMM project scientist, who provided this view graph. It's a very nice result. So my final result is the kind of universe result, and it's XMM's contribution to the hunt for the missing baryons. And you know, the baryons, we're only talking about 5% of the matter of the total energy density of the universe, but we don't know where all that 5% is in the local universe. In the distant universe, beyond about a redshift of 2, a lot of it's in the Lyman alpha forest, but it's difficult to see in the local universe because it's been collapsed and it's shock heated and it's tenuous. And so what people have tried to do is use distant objects as kind of lighthouses and look at the X-rays shining through this structure. And you can see an example here of a distant AGN B-lac shining through the structure, and that structure imprints absorption features on the spectrum at intermediate redshifts. And this is incredibly challenging to do. This is a 1.5 megasecond spectrum. That's many weeks observing of this distant B-lac. And indeed, you see 2 absorbers at highly ionized oxygen detected at intermediate redshifts. And this is indicating that we're seeing this structure. And when you do the sums, it appears that this is where a large fraction of the continuum lies. So that's a sample of the results. If we look at what XMM has achieved in total, it's over 6,000 papers, 6,000 referee papers that use XMM data. This doesn't include papers that reference XMM results. This is really papers that use the data or make quantitative predictions. And that is the most of any of the ESA science program led missions. It's less than HST, but it's more than everybody else. And I think that's a great, that's something to be very proud of for everybody who's been involved in XMM. You can see that in another way. This is a chart covering 20 years of the publications of all the science program missions, and they're listed from top to bottom in terms of when they were launched. So it starts in 2000, and this big red wedge that stayed pretty much constant for almost 20 years has been XMM. And I think it's quite remarkable that we're still getting 300 or so papers per year from a mission that's now 21 years old, and all credit to people concerned. And you know, I go on a lot about publications. It's one metric that you can use to quantify success. It's probably the simplest. It's perhaps the most informative, but it doesn't tell you a lot about the impact or even indeed the legacy of the mission, nor its impact on the public. So we also provide to RISA gets information on the total number of citations, and again, XMM is in the first place for ESA missions. The number of influential papers, which we deem to be those with more than 100 citations, again, XMM is in first place. The impact factor, the 2-year publication factor, I'll come to that in a minute, and the number of unique author names, and it's 16,600, which is again the largest, although Gaia is catching up very quickly. And a couple of statistical indices, the M and the H index, where XMM is in 4th positions. We're now starting to provide it metrics on science communications. So, I mean, it's been incredibly successful. And one of the things that's quite surprising is the evolution of the impact factor with time. So the impact factor for a particular year, let's say 2020, you look in 2020 for the papers that occurred that were published in 2018 and 2019, and you look at the citations for those in 2020, and then you divide by that number of papers. So it's the average number of citations to the papers in the last 2 years. And this is very much the typical shape. It normally starts high, drops fairly quickly, and then starts to level off more slowly. But what's happened with XMM 10, 11 years after the launch is it started to go up again. So that means that papers that are coming now are getting more citations on average than they did 10 years ago. And that's remarkable. It's unlike any of our other missions. And it says something about the quality of the science that the mission is still producing. So my last topic is why do I think XMM is so successful? And I think the first thing is almost obvious. It's that the spacecraft, everything has worked reliably for 20 years. The instrumentation is still providing competitive measurements after more than 20 years. And I think that's a tribute to the foresight of the people who developed the instruments and the skills of those who made them, so on. The fact that the science operations at ESAC and the instrument teams make sure that we've got efficient scheduling, the calibrations are very good, the data analysis software is very good, and it's all been updated. And the fact that we have a very efficient and a very professional missions operations center at ESOC. We sometimes forget these guys, and I'd just like to show you a couple of view graphs that say we shouldn't, because we often think of ourselves as scientists as playing a key role, but these guys played a key role in saving the mission. We almost lost, indeed we did lose the mission for a few days in 2008, and think how much science we'd have lost. What happened was that XMM-Newton has 2 antennae. They point in different directions, and you use the one that's pointing closest to the ground station. So every time you have a perigee passage, what we would do is load a time tank command to switch the antenna that you're going to use, because when you came out of perigee passage at the other side, when you got contact again, you'd be pointing in the opposite direction. So that command was sent up, and what it would do would change a switch from left to right, effectively. And so during an hour around perigee, you don't have any contact, and then it comes back again. And on the 18th of October 2008, XMM didn't reappear, and we didn't know what had happened. It's the worst case. You can't contact the thing. You can't start trying to understand the problem. A couple of days later, we got the first bit of good news. Some amateur astronomers in Starkenberg had made this image here, and this track here was actually XMM. So the fact that it was there meant it hadn't exploded. It was in one piece, it seemed. So that was good news. And the next morning, a very weak signal was picked up by ESA's 35-meter antenna in West Australia. It was too weak to command, but at least we knew XMM was there, and it was, it was still alive. And so what happened next was that a spacecraft emergency was declared, and we envisaged the help of NASA. and it was NASA's DSN, Deep Space Network, Goldstone antenna, because it turned out the perigee of XMM was close to the North American continent, and this antenna was fairly close. And what they did was beamed with as high power as they possibly could the command to move the switch back to its last working position. And that there was enough power to bridge the gap, and normal communications was resumed on the 22nd. Boy, were we pleased. I remember I was at ESAC at the time, and there were so many long faces because, you know, the mission was lost effectively, and it came back on. And I think, you know, we shouldn't forget the large number of engineers, the large number of people at ESOC and elsewhere who keep these missions flying, and we rely on them. Okay, so that's the first thing. I think it's almost goes without saying that that these things work well, and we're very, very reliant on. The other thing that I think is incredibly important is you guys, the community, the people who use XMM. It's both large and it's both high, and it's highly productive. And there have been something like 400 PhD theses that use XMM or report on the hardware development and so on. And there are every year something like 120 new first authors and 400 new authors of XMM. And this shows no evidence of decreasing. So there is a new community of young people coming in using the mission for the first time. And I think that's great. And this was a graph that Jan Uvenes put together some few years ago. And I think that the fact that we have this community is so important. And it's interesting to note that back in the time of EXOSAT, there was something like 1,100 unique author names on the much smaller list of EXOSAT publications, 800 or so publications. But the number of authors of XMM publications has grown by something like a factor of 15 during the time between EXOSAT and now. And something like 1,500 scientists are involved in each call. So this is a classic chicken and egg situation. Is the community so large because the data is so good, or is the fact that the data is so good as a result of and the publication is so good because the community is so big? I think it's a little bit of both, but clearly the community is one of the key things about this mission. And the third thing, and I think I hinted at this in the examples I gave of the mission, is collaboration. All those results that I gave were in collaboration with other missions, in collaboration typically with Chandra, with New Star, but with other missions as well. And it's that ecosystem of missions that come together that produce often the best science, the most interesting science. So it's the fact that XMM isn't alone, that it's used very creatively by the community in conjunction with lots of other facilities, that I think is one of the keys to the success of the mission. So I've got a couple of minutes left, so I'll finish on my last topic, which is the future. And these are some view graphs that the Athena study scientist Matteo Guinazzi gave me. The future is hopefully that we carry on making wonderful observations with XMM for as long as we can, to 2031 or around then. And that's limited by onboard fuel. And the people in charge of things try and minimize the use of fuel and maximize the length that we can operate this mission as best we can. The successor mission to XMM is called Athena. It's planned for launch in the early 2030s. It probably won't quite overlap with Athena, but it'd be great if it would. The mission is currently under study. It's in what's called phase B1, and adoption, which is ESA speak for final approval, is planned for mid-2022. It's not in competition with any other missions, but it has to demonstrate that it's got a viable mission, that the funding is in place, in the member states and elsewhere for the instruments and so on. And those are no mean tasks. And by mid-2022, we should have a final decision by ESA's Science Program Committee that we can move forward. It has a similar design to XMM in some ways, and in some other ways it's different. It has a single telescope rather than 3, but it has a larger area, 1.4 square meters, as opposed to something like 0.4 meters. It has 5 arcsecond energy width as opposed to 15. So that means the imaging size, which goes as the square of this number, is something like a factor of 10, or will be a factor of 10 better than XMM. And it has 2 instruments, a wide field imager, which is like a much, much better version of EPIC with better spectral resolution and better count rate capability, and a wonderful high energy imaging spectrometer, which will give us grating light resolution, but with imaging resolution and 5 arcseconds pixel. So it's very much focused on X-ray spectroscopy. So it's taking the heritage of XMM to the next level, I think, and it's going to be wonderfully exciting. And my final view graph is, well, those 3 success factors that we have, are they going to be with us for Athena? Well, the first one we can't quite fully say yet because we're not up there and testing, but most likely we will have superb instruments, optics, spacecraft, and a ground segment. We have a very experienced community building the instrument. ESA knows how to build spacecraft. The spacecraft isn't particularly difficult. The optics is very challenging, but work has been going on for that for many years. So I think most likely is that number 1 will be in place. Will we have a large and highly productive community to exploit the results? Yes, I believe we will. I think both XMM and Chandra will nearly overlap, or maybe overlap with Athena. So that will help keep the community together. In the meantime, we have eRosita, and we will have GRISM, which is going to be a wonderful Japanese NASA mission with ESA participation that's going to push forward on X-ray spectroscopy. So these will keep the community growing and becoming even stronger. So I think yes to number 2, the community will be there. And will there be opportunities for collaboration and joint observations? And I think yes. Again, the answer to that is yes. And there are lots of new facilities, SKA, the ELT, CTA, the Rubin Observatory will be coming on board, as well as LISA in the mid-30s. Multi-messenger X-ray astronomy, messenger astronomy is going to be one of the key topics in mid-30s. So I think, particularly if we can get the Theseus mission, which is under study at the moment, approved, that we will have a wonderful panorama of missions to work together to do wonderful science in the mid-30s with Athena and all these other missions. So that's my summary on XMM. I think I probably used up all my time, but I probably have time for a few questions. So thank you very much for your time for listening. Thanks. Over to you, Maurizio.
So, dear Arvind, thank you so much for your excellent talk. I know it's not easy to summarize, more than 6,500 papers in what are the highlights. But anyway, you went from solar physics, from a radiation belt on the Earth, to low mass X-ray binaries, to galaxies, and to even to the missing baryons problem in the universe. And also something which is very interesting, asking ourselves, it was an ESA cornerstone mission, and why this mission after even 21 years, is still so successful, attracting new generation, putting this together with all the missions. And I think it's a study case, what are the metrics to evaluate what is a successful mission or not. And I think you asked a lot of questions by also, which is very much interesting to take also XMM as a study case, for how to build the space science missions that it should be successful.
Yes. I think understanding what the factors are that make missions successful helps us choose in the future successful missions, and helps us operate the missions in a way that enhances the science.
So now to all the people who are listening, there were more than 140, and you have 2 ways now to ask questions. One is you can write your question in the chat, and I will read them to Arvind, or you can also raise your hand. And I see already one raised hand. By the way, John Czarnecki say thank you to you, Arvind.
Thank you, John. Good to hear from you.
And I have to say, I see really a lot of EC friends, and I am very happy to see so many people listening to this talk, which are also very familiar to EC. I think the first raised hand is by Roger Maurice Bonnet, who actually, Please, Roger. Can someone unmute Roger Bonnet?
Can you hear me? Yes.
Yes.
Thank you, Maurizio. Thank you, Arvind, for one wonderful talk, wonderful talk. Each time I am here in front of my computer and listening to the results coming out of the missions that you and many of your colleagues have made together with me, I am very proud. I am very proud and I'm very happy. I just had a question, well, comment first. You did not have time to describe that, but the construction of XMM really deserved a lot of impressive commitments with Robert Lenné and his team to build such a spacecraft, and the mirror in particular, which was, as you know, as you remember, a very difficult thing to do, but the result of that is absolutely outstanding. So I think these people have done a beautiful job. Now, a few years ago, I was working with the Herschel people, and they told me that the rate of publication of Herschel was beating every other mission, in particular XMM, the rate at which publications appear. Is that correct?
It was for a time, but Gaia has overtaken them all now. Gaia is by far per year, the highest of all the ESA missions. It's comparable to HST.
Thank you.
So there is also one question from Andrea, and he's asking which infrared observation has been taken to have it as a co-observation with XMM-Newton?
Probably the answer to that is with Herschel. They were flying 2009 to 2012. So that one of the three instruments on board Herschel, together with XMM. You can look into the ESA Sky archive and select those two missions, and it will come up with everything that was done together. So I should make a plug for the ESA Sky archive. It's a really wonderful archive of the sky in multi-wave bands, and you can investigate your favorite objects or your favorite missions and really see what they did and what they did together with other things.
We have one more raised hand from John Czarnecki. Hi, John.
Hi there, can you hear me?
Yes.
Hi, John.
Hi, Arvind. Thank you very much indeed. We've talked in the past about the number of publications, and I know you've done a lot of work on that, and I think it's extremely useful, though I think, you know, most people agree that it needs to be treated with some caution. I mean, partly I say this because one of the missions I was involved with is very close to the bottom of the list. And, you know, partly the number of publications is surely a function of the duration of a mission, the length of the observing time, if you like.
Sure.
So I think I've asked you in the past, and I haven't seen this yet, but I'm going to challenge you again. I'd like to see the publications normalized by length of observation. So let's say papers per day. And I think they might look quite different. I don't know what you think of that. You might also do by you know, papers per €1,000 as well. That the bean count.
I did try and do it the bean counting way, but it's very difficult to. I mean, when I was working in ESA, we knew the ESA costs, but we didn't know the costs of the member states necessarily.
Yeah.
And of course, the total cost of the mission is everything put together. So that was difficult to do. You're right in the sense that missions like Rosetta, Huygens, the impact was much higher than the number of papers would suggest. And I think that's why now we need to include measures of the impact, the outreach and so on, and look at those, because the outreach from Rosetta was just phenomenal. Same with Huygens. I mean, it really put Europe on the map. And that isn't reflected, as you say, in the number of scientific publications necessarily. So I think there isn't one statistic that you can use that gives you the picture. You have to look at a range of them and understand the limitations of each of them to really get a better view of it. Yeah, because otherwise we would just do it. We would just do observatories.
Yeah. Thank you.
We have one comment from Didier Barret, which we of course say hi to him, and telling, of course, thank you for your wonderful presentation, and that XMM was such a great mission that is putting actually pressure to Athena now, that Athena cannot do worse or have to do better actually. So
Athena is going to do fantastically well, as Didier knows. I mean, he's working incredibly hard on that project, and it's going to be wonderful. And I think much of the science that we learn from XMM and from eRosita and from GRISM are going to feed into the starting point for the science of Athena. But Athena will be the next step. It will take us on. And many of the things that it will discover, we have no idea about now. I mean, that whole parameter space of high resolution imaging spectrometer, we're really only beginning to scratch the surface of. It's going to be phenomenal. I look forward to it.
So I think we can stop here. I would like to say once more, thank you for giving this excellent talk. Of course, when we have a mission, as you already told, we have to say thank you to all the scientists, 1,000 scientists, and to all the hundreds or more engineers that are making such a beautiful diamond flying and keep it in orbit. And from the EC side, we are small and beautiful. I also would like to say thank you to the people behind the online Game Changer seminar, which are sending out the emails. Thank you so much, Andrea Fischer, for taking care about all this. I would like also to thank Saliba and Willy Waffler that they are making, that we can be online on internet and everything is working fine, recording them, putting them on the web, and making also that EC is working so smooth. And of course, thanks to all the EC directors and EC staff during this hard time that we cannot have all our visitors anyway, to bring a little bit EC through a web seminar out to you in this form. So thank you to everyone, and see you next week with, again, Game Changer online seminar with Göran Pilbrat about the Herschel mission. Bye. Bye.
Bye, Maurizio. Thank you very much, everybody.
Thank you.
See you soon. See you hopefully soon. Bye-bye.